change the file like way this? Because right now I just have all my history labs. So I can I guess I'll do this.
Can you land station? Or can I share with you?
You can share, but this desktop doesn't have the correct version anyway, so it's okay. Wherever you want to see, it's okay. You can see there as well if you want.
So is everybody using their laptop then?
I think so, yeah. It may take, I mean, probably 2 weeks for them to update every computer. All right, let's keep going with this tutorial for the lecture. It's nice to have a like 1 hour break, right, for lunch. Otherwise, your brain will just stop there, not working. All right. So let's just look at the first code. I don't want to move too fast on it. If you don't understand what's going on, since it's the first time you work with the Verilog script, I want to make sure everyone understands what's going on here, okay? So this is a module. So you have a declare a module here. I have to put an end module at the end to include everything in between. So test 1 is the name of the module, and these are the ports of the module. And you have to assign a type of the port, for example, input for these two and output for these two. Okay. So for assign, when you assign something, an operation, logic operation to something, okay, and what is the modeling method in Verilog if you are doing assign something to something and end it with a semicolon? So what's the name of the modeling method here? Take a look at the website and scroll up. Look at it, right? So how many modeling methods we talked about in the morning? Three, okay? Structural is you have an AND gate and then these are the ports. Let's take a look at it real quick. So structural, data flow, behavioral. So behavioral is always at something, right? It has a sensitivity list. Data flow is assign something to something, right? So structural is you have the keywords for the gates. It's like a function. And then you have the gate, the name of the gate. So this is the name you give to it, okay? It can be something else. But this will define a certain logical operation here. So the following the two at the end are the inputs, and this is the output. And this is the name of the gate. And this gate is doing an AND logic. That's a structural modeling method. And data flow modeling method is you have ports and you have logic operators and assign to something and use the assign keyword in here. So assign is a one-liner, okay? So assign something and you have to end it with a semicolon. So it's just one-liner. But in behavioral, like always add a sensitivity list. If something happens, you do the following. So these ones are multi-line statements. They are being separated by semicolon as well, but you can definitely have more than one line in it. If you have more than one line, you have to use begin and end. All right. If you don't have begin and end, but only have one line or have multiple lines without begin and end, what's going to happen? So you have always add something, you do a lot of things here, but you don't have begin and end. So what's going to happen? It's probably unclear here, but what if we have something similar like that? This is a initial begin and end. It's very similar. It's being used for the just above always to assign some initial values to some ports. If you have multiple statements in here, if you don't have begin and end, it's going to only execute the first one. But all the following ones will be ignored, right? Okay, so now let's move to the example we're going to work with, okay? So the logic here is pretty simple. This 20-second delay is being added to the module. It's inside the chip. It's being built in the chip. Is that clear? So the test bench is not going to affect that. So 20 nanosecond delay is in the chip. It could be multiple inverters. I have 100 inverters to build a buffer to delay that 20 nanoseconds. It's okay. It's just something in there to delay it. And if you want to assign some signals and also probe the output, you need the test bench. So here's the test bench. It's another Verilog file. So also a something.v file. So in this test bench, you have to include that module in it. So the module's name has to be exactly the same as the module you have. Okay, it's called test1. And you can rename it as whatever you want. You can call it UUT. It's a unit under test or something else. It doesn't matter. This is the name you give to it. Could you imagine why do we have to do that? So here's the test. This is a test bench. Okay, it's a test bench. I grab a chip. Right, I put a chip on it. Okay, here's the chip. I put a chip on it. Right. So the chip's name is called clip. Put clip here. Okay. So when I grab this clip, I have 100 clips in the drawer. Okay. I have one clip, and when I include it into the test bench, I call it clip. I put a clip here, so I know I'm having a clip on it. Right. Can I have another clip? Yes. In a digital circuit, you can have as many as you want. You can have multiple inverters, multiple AND gates, but they look exactly the same. They are all AND gates or clips or inverters, right? But if you want to differentiate between all these same gates, you give them a different name in the test bench. So that's why you can use the same chip for multiple times in the test bench. You have to rename it after you claim it. So that's why it allows you to give a different name to that little block. Test1 is the module you have over here. That's a block, that's a chip. Okay? And you include it into the test bench. I only have one, okay? So what if I want to include two of them? Two of these modules into this test bench. What should I do? So should I do a test1 and test2? What?
Test1 and then different.
Yes, test1, UUT, test1, UUT, or not? No, test1, UUT, test1, UUT2. Okay, what about test1 UUT, test1 UT? It's okay, whatever you want to name it. Test1 UUT, test1 Mason, it's okay, it's going to run, it's going to compile. Understand it? Okay. And you can make individual connections of all the ports of that chip, of that module with this is your test bench. So test bench is this a simulation, so that's why it doesn't have ports, because everything's within that simulator. Okay, but if you have an IPGA, if the test bench is the IPGA, you do need the ports because the name of the ports are keywords, you cannot change it. So if you are using a test bench, IPGA as a test bench, you are going to have a parenthesis, okay, the parenthesis, and the names of the ports in the IPGA are the certain names that cannot change. For example, CLK is the clock on the IPGA board. Or for example, switch, it's going to be SW something, SW0, SW12, SW15. So these are the names of the hardware on the IPGA cannot change. So these can be served as ports for the test bench if you are using the simulator with IPGA. I can repeat the question. So we only have one clock source, but you can divide that clock for different frequencies. So, for example, I have certain name of the ports. They are specific hardware available on the IPGA, okay? And I have to claim it if I want to use IPGA as a test bench. So it's going to be a parenthesis that have clock, switches, push buttons, like the 7-second display, the display ports were the decimal points ports or something else. So there will be ports for that test bench, but here is a simulator, so we don't need the ports. It's just everything being provided by the computer. It's like virtual ports. So we don't have parentheses to include the ports, but we do have register type data here and a wire data type here to either inject the signal to our chip, in the test bench, or probe the output from the chip. Okay? So I declared 2 inputs for the test bench, okay, and 2 outputs for the test bench. And I define that the 2 inputs are register type and the outputs are wire type. Why I want to do that instead of the other way? If you look at the code, I think I talked about this very briefly in the morning. Why do we want to make the inputs as a register type instead of wire? But output doesn't matter because it's just a metal, right? I just need to probe it. Just a wire, just a piece of wire. But the input need to be register type. Why is that? You can set them. They can store some value to them as initial values. So that's how we do it, right? Initial, begin, and end. So these are the initial values that I give to these ports. However, you have to know that initial if you only have one line of code or statement, for example, it's not applying to this code. I'm doing a totally different code type of script that I only need give 0 to init in 1t. Okay, let's just do those. Initial in 1t, and I give a 0 to it. Is this correct? Syntax wise?
Why give the initial begin?
Yeah. This also works if you have only one line of statement. If you have multiple lines, you have to use begin and end to wrap them up. You know what I mean? If you have multiple lines, right? 1, 2, 3, 4, whatever. If more than one, you have to use begin and end. Okay, otherwise, it's only executing the first line. If you have multiple lines, it's only executing the first one. But initial and just one line and semicolon also works. Keep in mind. Okay. So initial begin is not one term. Okay. Initial is one and begin end is another one. So that's how you know that everything here will be executed once. The reason is the initial statement will only be executed once in Verilog. That's another thing you need to know. It's only being executed for once. However, you can repeat it for a few times if you have a repeat statement. For 4 times, it's going to do this for 4 times. So the statement in test bench is for simulation purposes. So you're actually writing up it's something like the SPICE code for simulation. Okay, it's not a synthesizable hardware or digital design. Probably you are thinking about, hey, you just talk about the digital designs. Everything is being implemented on the hardware for once, right? Why is it able to repeat for so many times? This is just simulation. It's not synthesizable. You cannot make a hardware just based on this test bench simulation code. It's only for simulation. But for the code here, okay, if you remove, I'm not sure if you can do this 20-second time, it depends on different IPGAs. But if you remove this 20 nanosecond time delay, so for the entire module here, what I wrote here, right? So for what I wrote here, the entire piece of script is totally synthesizable, which means the compiler will be able to convert it into a list of the connections and implement the hardware, the physical hardware on the chip. So this can directly become a hardware on the chip. But the simulation is not. Simulation is just based on your laptop or your Windows operating system. Okay, this is nothing physically implementable. But if you have a test bench, the FPGA version, right? You have all the switch and the clock, whatever in there, and that won't allow you to do the initial begin or something. It won't allow you to do the 100 nanosecond time delay if you are using an FPGA. So in that case, it's definitely implementable or synthesizable. You can put on the FPGA. This is just for simulation, okay? And another thing you need to know is, so in here, in this parenthesis, all right, the purpose of that one is you include that submodule into your test bench and you rename it, okay? And immediately after that, you want to make a connection because your test bench has wires. You can think about like you have a test bench here. If you want to connect to the oscilloscopes or power supply or the function generator, you need the wires and you need the connections. So that's how you do it here in Verilog. You have to put a dot in front of it, so which means you are starting a connection. So dot and followed by the port or the wire or whatever the register type, data type wire connector connection from your sub-module, and then another parenthesis to include the port or connector you want to connect to in the test bench. Sounds complicated, but let's do this one more time. So the purpose of this one, okay, this line, is first you have to include, you want to include a sub-module in here, and second, you want to rename it, and third, you want to make the connections, okay? So the way you make connections is you put a dot at the beginning, excuse me, and followed by the port from the sub-module or from the test bench. Very quick question. So Alt1 is a port from the sub-module from the test bench. Sub-module, okay? And then it's being connected to the port in the test bench in the parentheses, okay? It's the same principle just being followed by all the other ports or the other connections. Okay, is that clear? So the first one will be the connector or the signal in your sub-module, okay? All right, so after the connections are made, you move to the initial beginning, you start assigning signals to the signal line in the sub-module or signal lines of the test bench. So test bench, you are right now inside the module of the test bench, not the sub-module. You cannot directly control the things in the sub-module. You can only do it, operate all the signal lines in the test bench, right? So assigning initial values to the test bench, and you delay it for 100 nanoseconds, and don't forget to put a semicolon on it after that. So we are ending that line. It's going to be just a pure time delay without doing anything else. It's going to be a pure time delay. And then repeat. After repeat, did you see a semicolon? No. So which means it's not ending yet. So all the following ones are actually following this repeat. They are still within the same statement. So repeat for 4 times. So which one is being repeated for 4 times? This one. Did you see a semicolon here? See a semicolon here, but did you see a semicolon here? No. So it's going to be 100 nanosecond time delay and immediately followed by this assignment. So it's going to change the signal of the 2 bits. If you use a curly brace here, it's a concatenation. Name of it? Concatenation. Is it combining? Yeah. Concatenation. Yeah. It's combining these 2 binary numbers into one 2-bit binary number. And you're adding a 1-bit prime is a 1-bit binary number, and which is 1. So the value of the number is 1, and it's a 1-bit binary number, and the value is 1. So you're adding a 1 to the 2-bit binary number. What's happening? It's just adding a 1 to it. Okay. So it starts with what? So what's the starting value of the 1 in 1t and in 2t. 0, 0 because it's here, right? You're adding a 1 to it after the first cycle, you're getting a 0, 1, and then 1, 0, and then 1, 1. Okay? So we're trying to change the 2-bit binary values for 4 times just to verify the logic. Okay, so then you have an AND. So the AND is serving which one? It's serving module or serving initial? Begin. Yeah, so this one serves initial begin, okay? And then end module will end this module. That's the entire test bench module, okay? And now let's see if we can just hand draw that simulation or the output here. So if you don't have a test bench, nothing is gonna happen. So the chip is just a chip, doesn't have a signal input, right? So if you delay everything so you give 0, 0 to these 2 input lines. However, for the test bench, let's start from time 0, okay? Start from time 0. So initial begin will assign initial values at time 0. Okay, if we start from time 0, the values for in 1t and in 2t will be sent to in 1, in 2 for the submodule. Is that correct? Because they're interconnected, right? So what is L1? At time 0, what is L1? Is that 0? 0 and 0, 0. 0 or 0 is still 0, right? And 0 XOR 0 will be 0 because they're the same. So XOR exclusive ORs are still 0. So L1 will be 0 at time 0. What about L2?
It'll be the weird undefined.
Yeah, it will be nothing, undefined, unknown, right? For how long?
20 milliseconds.
No. 20 nanoseconds.
No.
Yeah. Right? So after 20 nanoseconds, L2 becomes 1, right? So you can already draw something, right, up to 20 nanoseconds or even after for the all signal outputs. And L1 is shorted to L1T, L2 is shorted to L2T because we did it here in the test bench, okay? So if you probe L1T and L2T, you will be able to see that.
Since the assignments aren't happening sequentially, we have to include the time of the first assignment as well.
The time of the first assignment, which one? This one?
Back up on the last picture you were on, because we're not assigning them sequentially, right? So wouldn't however long assigning out 1 takes be added on to the 20 nanosecond delay as well?
For L1 or L2?
Out 2. Because it'll assign out 1 before starting the 20 nanosecond delay, won't it?
Yeah.
So it'll take like an extra nanosecond to assign out 1, and then we have 20 nanosecond delay in that the assignment, right?
L1 will take effect immediately.
There's no hardware delay involved in.
Oh yeah, we don't consider that. It's just simulation. Yeah, ideal. Okay. Yeah, all the delay are man-made. We just added to 20 nanoseconds. It's gonna be perfectly 20 nano.
Okay, I was just wondering for the timing chart if we had to include the extra delays that are happening sequentially.
Did you mean the time delay you are expecting from the hardware, or time delay for?
Well, just because Ryan, like lower down in the assignment, you have that chart you drew out of timing.
Yeah.
So there's the 2 ways of assigning the variable, one with the little pipe headers so they occur sequentially. But wouldn't this one run out the assignment of out 1 line and then after that finish?
No, they do it at the same time.
Oh, I thought that was with the other.
That's not a blocking and non-blocking, it's just a sign, it's not in the behavioral. So the blocking and non-blocking only happens to behavioral.
Oh, okay.
Yeah. So all this is combinational logic for the data flow modeling methods. That's why we need to know the 3 different methods.
Right.
So the non-blocking blocking only happens to behavioral, not data flow. So data flow have all the assignments. They are not executed from top to bottom. They are like conventional logic being assigned at the same time. That's how you design the hardware. It's like the everything you write here will be directly translated into a gate level circuit you can draw on LT-Spice. You can imagine that if you have that kind of circuit, if you keep the simulation button on LT-Spice, it's going to run at the same time. You won't have any delay. It's a hardware. So it's different from C or C++. Yep. Good question. All right. So the first 20 nanoseconds, we know what's going to happen. Okay. So what about after that? And also this is behavior, and we are not considering the time delay from this and this. It's minimal. We are not considering that. So what about after 20 nanoseconds? What's going to happen just based on this?
It waits 400 nanoseconds.
That has to delay for 100 nanoseconds first.
Right, but then doesn't it just repeat itself 4 times?
Yeah. So, but before that, you have to delay for another 100 nanoseconds first. Yeah, for this one, right?
Is the repeat doing the line below it?
Yes.
Oh, I thought the repeat was repeating up to the initial peak.
Yeah.
No. This only manages whatever follows it. But after the previous semicolon, that's why you need a semicolon to end that line, to end it. So you are starting a new thing. Okay? That makes sense? Okay. So repeating this thing for 4 times. So for the first time you do this, you execute this one, it will add 100 nanosecond time delay first, and then add a 1 to it. So if you add a 1, this becomes 0, 1. Becomes 0, 1. And then you come back here. If you have 0, 1, right? So in2 definitely has changed because it's been flipped. It was flipped, right? So out2 becomes 0. Okay? But out1 becomes, it's going to be a 0, 1. So this is 0, this is 1, and it's going to be 1. Okay? So out1 will be flipped, and out2 will be flipped as well. And that happens how many nanoseconds after that 20 nanosecond time delay? 200. Is that true? Yeah, it's going to be 200 nanoseconds after that. However, after the first time of a flip of the data, it's going to stay here and repeating this for 3 more times. Okay? And you're only having 100 nanosecond time delay instead of 200 after that for all the changes. Does that make sense? It's going to be, you have to stay at the previous data level, the voltage level first, and for 100 nanoseconds, and then do some changes according to the logic. So after that 100 nanosecond time delay, and if you want to have anything changed to L2, when that is going to happen? So within these repeating times. So this 100 nanosecond time delay, you cannot change it, right? It's going to delay for no matter what. It's going to stay there for 100 nanoseconds, okay? However, after that, your L1 will be changed, okay? But your L2 will wait for a certain amount of time before it's being changed. So how long is that time? Do you understand what I'm saying? So your this 100 nanosecond time delay is being added from the test bench. There's nothing to do with the internal structure of the module. So it's going to delay for 100 nanoseconds to do this logic, to change the signal over here. all right? After that signal has been changed, your L1 will be changed because based on this code, right, L1 will be immediately changed because these signals are changed, okay? And then you have to wait for another amount of time until L2 can be changed. So how long is that? 20 nanoseconds, right? Okay, if you are using 100 nanosecond blocks, so when you're drawing your timing diagram, if you're using 100 nanosecond time blocks, right? Okay, so your L1 will change immediately, right? Whatever is going to change, but your L2 will wait for 20 nanoseconds and then do the change. You know what I mean? Every time. Right after that, okay? It's going to change after that. Make sense? Okay. So now you know how to draw the timing diagram, and so we can compare it with your simulation.
So is the 20 seconds or 20 nanoseconds within that 100 nanosecond block, or is it added on?
It's within.
Yeah, I'm saying like in that 100 nanosecond wait,
Yes.
it's on the same line.
It's within the same 100 nanosecond time block because that's the time period of your output signal changes, right? If that changes, it's going to change the signal being injected into the chip. So it's just whatever the chip is doing inside doesn't affecting the outside force, right?
Yeah. So if you had like a 100 nanosecond wait and then the process itself took like 120 nanoseconds, would it?
It's going to move to the next cycle, I think.
Okay.
Oh no, it will never. It will change. I think it's still waiting for it's going to wait for another 120 nanosecond time before it's able to respond to the next cycle of 100 nanosecond. You know, it's just super delayed. It will still do the job, but it's just being super delayed.
Okay.
Yeah. It's like the time you wait for the shipment, right? So if you order things from Amazon, right? You wait for a certain amount of time, but when you receive it, you'll still do the job. You'll still use it to do your things, right? But it's just you have to wait. Yeah. All right. So we can do run the simulation and compare with your hand drawing. And there's another way to make it easier. If you don't want to create multiple .v files, you can just keep typing in the same .v file, the same window, but different modules, right? They're not affecting each other unless you intentionally want to interconnect connect each other in a certain way. So if you look at this script, I have module and module. This is one chip. It's an AND module. It's an AND logic and gate. I have three ports, two inputs and one output. And this is the operator. That's the AND logic. And I define another module within the same window. It's an OR gate, module and module. Okay. And I got the third one. It's called first system. And I have this is not a test bench, okay? But this module is showing another layer outside of that two gates. So outside of the first system, there's another layer wrapping it up to giving signals and probing it. It's serving as a test bench. You know what I'm saying? You can have like 100 or 1,000 layers. Nobody cares. So I have AND gate. I got OR gate. Okay. And I have another module. It's a different name. It's another module. Okay. And I have two inputs and two outputs, let's say. Okay. That's module. I think I call it first system. Let's just keep calling it first system. And this is called AND. This is OR. You know, if you look at the format, it looks exactly super similar, just the module and unmodule. Okay, first system has ports. This has ports. So this one is connected to here. This is connected to here. You can definitely use the dot parenthesis something, right? You can make the connections, no problem. Same to this one. So this one is shorted to here and shorted to here, and this one is shorted to here. This one is shorted to here. Okay. So it's just being nicely organized. You can have a bigger chip wrapping up smaller ones. So for example, you have another first system, you have a second system, you have a third system, right? And being distributed on the chip. It's just showing you a way to organize all the digital blocks. And maybe there's a bigger module to wrap up all these sub-modules called a big system. You can have another system called tiny system, whatever, right? So it's having different hierarchies of digital blocks, and eventually have everything being included into one bigger digital block and call it test bench. So that's how you organize all the digital chips. So this example shows you a really good example of putting all the different layers together and how to interconnect them. So this is a really important technique. Okay, so my question is, how do you interconnect? You got a wire here, got a wire here, right? How do you connect these two together? If you think about the code, you have different modules. This module and this module, okay? And you are including them in one test bench. Not too many, let's just make it easier. Just one test bench. And you are including each of them. This is the first system, this is the second system. Different module. So you can imagine when you do that, it's going to be a test bench, right? When you are including each one into the test bench, it's going to be first system UUT, okay? Second system UUT2, okay? So you can connect these ports to the test bench that we have been showing you how to do that, right? You have a test bench of ports. Let's just give one example. This is in 1T, and this is in 1. Okay? So when you declare or when you include this first module into your test bench, what does the code looks like? So I'm including this one in the test bench, okay? So just look at the line 1 included. It's going to be first system, right? UUT, unit under test, and processes first, right? And dot, so you are telling Verilog you are making a connection. In 1 should be connected to in 1T. Okay, this is one of the connections. I can start a new line, it looks cleaner, right? Like in 2, in 2T. So on and so forth, and then parentheses and the semicolon, okay? And let's make it shorter. And for the second system, this is another module I'm include into this test bench. It's going to be second system UUT2, right? Let's call it input. Okay, so I'm trying to connect this one to in 2T. Okay, so it's going to be dot. You can actually not call input, that's a keyword. It's called in3. So in3 is connected to in2T. Right? However, I want to connect these two together. How do I do that? I just connect these two together. I just want to do that for some reason. Okay, this is called out1, is out2. I mean, you are including this subsystem in the test bench, so you are now working at this level, right? Hmm? Reg out. But how to connect? I mean, what kind of statement can you use to register a wire? Yeah. So, but what are the details? That's the correct direction. Yes.
REG space out1, comma out2.
Yeah, this is declaring these two variables, but not connecting.
Oh, does it not connect those two?
Is something to do with that UUT?
Yes.
Is it UUT parentheses one dot?
Which UT? This one?
Yes.
That's right.
I don't know.
That's a pretty legit way to do it. I mean, if you are inventing a new language, that's going to be a great way to do it. But people can understand it when they read it, right? Yeah. So it's very close actually. That's the same idea. But the syntax of the Verilog use a different way. For example, this is called the test bench TB, right? We'll call it TB, and semicolon because the simulation doesn't have force. Okay. And we can declare a wire. We call it out X, for example. Okay. So this will generate a wire in your test bench. It's just a piece of wire. It's not connected to anywhere. Because if you follow the format of the including the UUTs into your test bench, you have to follow that. This is from the sub module, right? And this is from the test bench. You just have to follow that format. So now you declare a wire in your test bench, so you have something in the middle to connect to. Okay. If you do this and you do this, then you're done. Does that make sense? So both of these two signals connect to the same wire, so they are indirectly connect to each other. So how do we implement it in here? Can anyone do that?
Do you even need a new line, or can you just replace the in1T, in2T with that out X?
In1T, into T.
Like
These are inputs, these are outputs, the different wires.
Or sorry, oh, I see.
Yeah. So if I generate a piece of wire in the test bench, I call it out X. And I want to connect these two ports inside the test bench. Here. That's the right. $99 points? No. What's the problem? What?
99.
Yeah, 100. You get that? So because we have, this has to be the first one following the dot has to be something from the sub module, right? So for the first system, you got out1 from the sub module, and for the second one, you got out2 from the sub module, right? So connected to the wire in your test bench, you connect to the wire in the test bench. They are the same wires, so they are interconnected eventually. So you can do that connection that way. It's a very important technique to be used in Verilog. So if you understand that, this will be very simple. Does that make sense? Yeah. Okay. I'm showing you the interconnections, and for the first system, I do have a wire flowing in the middle from the test bench, so I can make connections to that wire in order to make the interconnections between the sub modules. And you want to use the vertical, the vert new, the column vert new, and the name file name, to split the window into 2 columns. To type your test bench in it. So in Vivado, okay, so the way to add your .v file into your project is you select add or create simulation sources, and then it's gonna have a pop-up window so you can find out the path and eventually the files and include it into your simulations. You are going to see these a little dot in the front, and then the modules, sub-modules in your test bench. If you see errors, you have to go back to your .v file to change it. And then run the simulation to verify the logic. And that's it. So for the tasks, task 1, use GVim and Vivado to simulate examples in sections 2.1, 2.2, 2.3. This is repeating the work. Post snapshots of GVim windows and Vivado simulation results in your simulations, 20 points. Run the simulation to show the difference between blocking and non-blocking assignment in the example in 2.4. Okay, so I think I didn't talk about the details of it, but so the goal of that one is just to show me that blocking and non-blocking is going to give you different values. So what's going to happen for this example from the textbook is, so the first 3 lines are blocking assignment, and these are non-blocking assignment. So the blocking assignment will give x to y0, right, and y0 to y1, and y1 to y2. So eventually y2 is going to host, you're going to hold the value of what? Yeah, but one step further, x, right? For the non-blocking, nobody cares. It's just going to do their own job. So y3 is going to hold x, and y4 is going to y3. So before y3 changes. So y4 is not going to hold x in there. So it's going to be whatever y3 was. If you don't specify that, oh, I think you do, because you are assigning 6 bit zeros to a y, so it's going to be all zeros, right, for all of them. I think you need a test bench for it. I have to write a test bench for this for this example. Could you do that? I think just use very similar things, because this is just a module. If you want to show the simulation results, you have to assign values to x and clock from the test bench. So clock could be, it's just the name of the port, right? You can just give use a repeat, and you give clock once, or just flip it or invert it after a certain time delay, like 20 nanoseconds. Is that clear? So for example, the clock, what you can do is, just do this. So in your test bench for that example, okay, I mean, we don't need to change x, right? It's a very simple example. We can just do initial x is 1, okay? And then we do initial, we can put them in 1 probably. Initial begin, end. So begin, you just give a x to 1 here, and then you repeat for 4 times. It could be 3 times, doesn't matter. It should be for 4 times. You add a time delay here first, like 20 nanoseconds, and followed by flipping clock. Just use this one for the test bench. So this is gonna invert clock every 20 nanoseconds, right? So you're expecting a clock signal like this, right? So this is gonna be 20 nanoseconds. So always at the rising edge of the clock, it's gonna update the values over here. So we will see a waveform in a simulation, because simulation has a x-axis as a time. So we're going to see something on the time in the time domain. So in your test bench for that example, you have to what's the name of the block? It's blocking, non-blocking, right? You have to include it there or instantiate it there. So it's going to be blocking, non-blocking, followed by what? Yeah, UT. All right. Yeah, since you have the ports, right? You need a X clock and Y being connected to your test bench, so you can give values to it. Because within that block, Y is already given, so you don't have to do anything to Y, I think. You can create, because you're giving X the 1 and you're giving clock. You need to give clock something as well at the very beginning. So let's do clock is 0, for example. Okay. So in that case, you need a register type of X and clock, right? Comma. So for UUT, so we're not making a difference here, which is bad. Let's give a different name. So register, that's in the test bench. Register, I want to connect something to X. So I just call it XX, okay? And clock, 2. All right? So in UUT, what you need to connect? It's going to be 1X or 2X first. 1X, connect to what? CLK, connect to what? Cardinal. Yes. Okay. And on top of it, it's going to be a blocking, non-blocking test bench. You give a name to it, semicolon, and it's going to be a module, right? N module, just add things to it. So it's going to do the work. Put them together and run the simulation.
Does that mean a semicolon as well?
Where? Oh, here?
Yeah.
Yes.
Okay.
Yes. Thanks. Cool. All right, so one more question here. See if you guys are getting everything. So why do we need a an oscillating clock.
So
The change needed by what?
always.
The always, yes, it's a pulse edge, which means the rising edge. So detecting the rising edge to do all the following jobs. If you don't have the rising edge, nothing's going to happen. Clear?
So with this piece of code, since it's always on the positive edge, it's just taking one input from X. Is it just stay constant after it changes then?
Because we are trying to see if, yes, it won't change always, but the S is not being changed, right?
Yeah.
But for the code, you want to compare the 6 bits because you want to compare the different results from the non-blocking and blocking. That's the purpose of it, right? Yeah, X is not changing. Yeah, after the first assignment, all the following ones will be the same. Wait. No, because this one, yeah, this one will give a 1 to it, but this is 0, right? So for the first cycle, it's going to be 0 for this and 1 for this, right? But after that, this has been updated. So after the first cycle, there will be all ones, right? But for the first one, it's a blocking, so it's waiting for Y0 to be updated. So Y0 will be 1, Y1 will be 1, Y2 will be 1 as well at the first cycle. So you'll see the difference. All right, let's see task. That's task 2, right? So task 3, repeat the simulation example in 2.5, which is the first system stuff we talk about. Easy. For the example in section 2.5, move 20 nanoseconds delay from move that from from line 25 to 24. Yeah, just change something and see if you can get the correct results to 24. So move this one to the top to the line above it and see what you're getting there. So hand draw the timing diagram like what I did here. Remember the time delay after time delay there will be a dot. So the dot is the operation of the logic expression. You need to label that change after the time delay. And 5, use the GVM and Vivado repeat example in 2.6. Post the GVM windows and the Vivado simulation results for credits. Okay, so followed by the examples of the commands, the very frequently used commands for them, and you can expect some of them will be tested in the quiz on Tuesday. And as everything about the tutorial, if you go to the lab, it's easier. Okay, it's pretty much has a lot of overlap between the lectures tutorials. It's two tasks, but you are just yourself. You are not assigning this to different people. There's a certain overlap. Okay, so if you have a laptop, please add Vim to the path environment variable, so you can directly use GVM as a command in your command line. Okay, so these are the examples of the commands that you are expecting during the quiz. And the last one is so these are the tasks, right? So it's mainly about the using the website as your lab report place. So you can have an example here for Taylor Nakai's website. You can see how he organized all the courses. Please follow that format if you don't have a better idea on how to do that. Practice GVM, prepare for the quiz on Tuesday. And you need to record a video of showing the commands that you use and record it. You can use any monitor screen recording tools and upload to YouTube. So it's a time for you to open up the YouTube channel if you don't have one. And use the YouTube videos in that code, HTML code, to put into your report. So I'm expecting a window with a video that I can directly click and play instead of a link directing me to the YouTube website. Otherwise, you will get some points off until you fix it. And install Vivado. So whenever you spend the time today to install it, you are getting credits. You can also use Vivado on the cross it, make a snapshot of user interface, insert a figure, so showing me that you are using GVim, using Vivado. Refer to the tutorial on the website. So the lecture tutorial and the lab tutorial doesn't include the details of how to open it up, how to load all the details, the parameters into Vivado. You have to click this link to get to the basics. I think most of you already used it in your 241 class. But if you forgot how to do it, come back to this web page and follow the steps over here to set it up at the very beginning. Okay. That's everything I want to talk about today. So you have almost a week to work on it from today. So it's due next, so the lab is very simple. So the lab is due next Wednesday at 10 p.m. If you look at the timeline here, so all the labs are due one day before the lab at the night, so 10 p.m. But the longer one, the class, the lecture tutorial, the basics, this one is due next Thursday, right before the class. Is that clear? Any other questions? So you can get started? All right.